Let's try a 3 by 3. X minus y plus 2z equals 0. 3x plus 2y equals 0. Negative 2x plus 2y minus 4z equals 0. Now you can go through the long way, or of course, if you are allowed to, you can use your calculator. So this is really, if you do the augmented matrix, a 1, a 3, and a negative 2, a negative 1, a 2, and a 2, a 2, a 0, negative 4, and the equals is 0, 0, and 0. So we're going to use matrix A, B, C, and D. First of all, the D matrix. Second matrix, we're going to edit matrix D. This will be D. This is a 3 by 3, and it is without replacing this. The 1, negative 1, 2, the 3, the 2, and the 0, the negative 2, the 2, and the negative 4. Get out, second quit. Get, back in second matrix. Now we're going to edit A. So this is D, and the D sub x we're going to call A. Okay. 3 by 3. Replace the x column, x, y, z equals, with the equals. So this is going to be, and you can use the arrow keys, 0, 0, 0. You might have to use the entry key to get to the right. But now this is going to be a negative 1, a 2, and a 2. And here's where you use the enter key to get to the right. And the 2, the 0, and the negative 4. So check it up, make sure. Here's a 0, 0, 0 replaced. Negative 1, 2, 2, 2, 0, negative 4. That's what A is. Could we get out? D sub y is going to be B. Get back in. Edit B. It's a 3 by 3. Now leave the 1, 3, and the negative 2 alone. Press enter to get to the right. We're putting zeros for this. And the 2, 0, 4. And enter when you're all done. 1, 3, negative 2, 0, 0, 0, 0, 2, 0, negative 4. Uh-oh. Okay. See, it's good to catch yourself. Get out, get back in, and we're going to edit C. It is now going to be a 3 by 3. Leave X and Y alone, and Z, oops, D sub Z is C. 1, 3, negative 2. 3, negative 2. 1, 3, negative 2. Negative 1, 2, 2. And now these are all 0, 0, 0. Better check them to make sure I didn't make any silly mistakes, so I can quit. And now we can take d sub x, which is really a over d, b over d, and c over d. So we go back in the matrix, a divided by, go back into the matrix, d, number 4. Oh, gosh. I'm glad I made that mistake. These are matrices. You can't divide matrices. You can divide their determinants. So let's clear this out. We need to go into the matrix and use the math determinant. Go into the matrix A, close that, divided by, go into the matrix math determinant. Go into the matrix D, which is number 4, close. Now we can divide the determinant. Oh man. Divide by 0. Uh-oh. Let's see here. Let's find the determinant of D. Matrix, math, determinant, matrix, D. Ooh. So, what does that mean if we're dividing by 0? You can't solve this system. It doesn't cross. The bad thing about Cramer's rule is that if that denominator's determinant d is 0, you really don't know. It's either inconsistent or dependent. You don't know which until you use a different method. So we need to now talk about a few more things. There are some theorems, properties of determinants. If you switch 2 rows of a determinant or columns, it doesn't matter, the sign, plus or minus, changes. So if it was a positive 5, it'll become a negative 5 if you switch 2 rows or columns. If a row or column is all zeros, then the determinant is 0. Well, we had all zeros here for this column, but you didn't have it all for D. D is the one that's going to be the big problem because it goes in the denominator. These numerators can be 0. One of your answers can be 0. So 0 divided by something that's not 0 certainly would give you something that works. But not D. That's the only one that messes you up. So if any row or column is all zeros, the determinant is 0. Easy to figure out then. If 2 rows or columns are equal, exactly the same, then the determinant is 0. If you multiply any row or column by some number k, then you have to multiply the determinant by k. And lastly, if you multiply a copy of a row or column by a number, say k, and add it to another row or column, the determinant stays the same. And that's why you're taking a copy. You're not changing the row. You're taking a copy of one row, multiplying it, say, all by 2's, adding it to another row. It doesn't change the determinant. Sort of interesting. It's when you add a multiple of another row that doesn't change. So, with that in mind, suppose you had x plus 3, y plus 6, and z plus 9. For your first row, 3u minus 1, 3v minus 2, and 3w minus 3, and 1, 2, and 3 for your third row. How would you find the determinant if you knew that x, y, and z, u, v, and w, 1, 2, and 3, this determinant, not matrix, but determinant, was 4? Well, let's see. We know this determinant. What did we do to this first row? We took a copy of this row 3, multiplied by 3, and added it to row 1. And number 5 says, that doesn't change the determinant at all. For this second one, we multiplied the row by 3. So we have to multiply the determinant by 3. But then we subtracted a copy of this row from that. You can say multiplied by a -1 and added it, same thing. That doesn't change it, but the multiply by 3 does. And then this row we left alone. So the only thing that really changes, because this is the same, and subtracting the 1, 2, and the 3's, taking this times a -1, remains the same. This one didn't change. So this is 3 times 4, or 12. And I didn't have to know what x, y, and z were. And that's section 12.3, Systems of Linear Equations using determinants.